First, I'd like to thank the organizers of this exciting and visionary event and for giving me the opportunity to speak to you tonight, which is really a thrill. To paraphrase John Bell, I'm a quantum engineer on the weekdays, but a historian of quantum physics on Sundays and quantum anniversaries. Here's an example of my weekday work, strategically chosen because the word quantum is in the title twice. So my reason I'm here today is because I did write a book and study Einstein's contribution to quantum theory some time ago, and I've been fortunate to have Alain Aspect as my European sales rep for that book. You got your royalties. Okay, so building on that book, but not sticking to it, I'm going to give you a sketch of quantum theory up to 1926 with an emphasis on wave mechanics. I want to begin by saying that the discovery or invention of quantum mechanics was a turning point in human civilization. We cannot imagine our modern world without the revolutionary science that was done there. No previous civilization had ever understood the atom, the microscopic world, and the fundamental constituents of matter and energy. This is a tremendous achievement of our civilization, and we should be celebrating it 100 years later if people understand how important it is. Now, this success was after 2 decades of frustration because although the search had begun, it had not been successful after Planck's work into the 20s, and a number of people really questioned whether it was possible for humans to understand this unseen world of the atom. And on top of that, there was this sort of philosophical view that was fading, but there was still a feeling that maybe atoms weren't real at all. Einstein mentions this in his autobiography, and that it was somehow unscientific to talk about these unseen objects. So Whirlwind Tour is what I'm going to do today. For a fuller story, I recommend this two-volume work by Duncan and Jensen. Now, setting the stage, atomic theory prior to 1900, here are these giants of statistical physics that you all recognize. They worked on gas theory based on the atomic molecular hypothesis started by Daniel Bernoulli earlier, and by 1852, Clausius had actually accurately calculated the mean square molecular velocity u, and it's described by Maxwell as a wind comparable to that with which issues from the mouth of a cannon. So it's a very fast speed, and how it depends on temperature was known. And then Maxwell and Boltzmann proved this strong relation that the kinetic energy of a gas molecule was independent of its mass. And this then was generalized to the equipartition theorem, which in modern language we say is kT over 2 of thermal energy per quadratic degree of freedom. However, this theorem, which was very helpful and many things were explained in the gas theory, was unable to explain the specific heat of gases due to the freeze-out of vibrations that we now know arises from quantum mechanics. Here's a nice quote from Maxwell already in 1875 saying, "The spectroscope tells us that some molecules can execute a great many different kinds of vibrations. They should have far more than 6 variables, and that should increase the specific heat, but this isn't observed. I have now put before you what I consider to be the greatest difficulty yet to be encountered by the molecular theory." Now, the general approach, of course, was they thought there would be new molecular forces and atomic forces, but that Newtonian mechanics and Maxwell-Lorentz electrodynamics would hold, and that's how they did their research. There wasn't much further progress on gas theory. I didn't tell you all the wonderful things they did do, but the real breakthrough, as you all probably know, came from thermal radiation. The problem that was identified by Kirchhoff in 1860, that there was a energy spectral density of an idealized black body, which was a sort of universal thermal electrodynamic quantity, electromagnetic quantity. A big leap forward was made by Wilhelm Wien in 1894 to 96, when he found the form of that function should be as shown here, nu cubed times a function of nu over t. And then he conjectured shortly thereafter that the function was just an exponential of nu over t. And Max Planck took over, saying that this was a problem of general interest, of universal interest, and he wanted to get involved. He was able to prove a relationship between the spectral density and the average thermal energy of a single oscillator, what I'm calling U sub res here. And a thermal oscillator was a charged harmonic oscillator. So he doesn't then invoke the equipartition theorem in order to get the answer, because this would have given him the wrong answer. And instead, he thinks he proves the conjecture of Wien, and only to learn just a year later that the experiments disagreed so strongly that he had to abandon his guess, and amazingly is able to just intuit or extrapolate the correct form of this. But then he searches for a derivation of this. By December, he's come up with a statistical derivation where he finds the entropy of thermal resonators using Boltzmann's relation, S equals K log omega, OW, which is the number of states. And this is the famous formula for the thermal energy of an oscillator that he comes up with. He introduces two fundamental constants, K, Boltzmann's constant, which Planck called Boltzmann's constant, not Boltzmann, and H, which has no name then. And he uses it to fit to the black body law and find the value of Avogadro's number and the charge of the electron to 2% accuracy. And he also finds H to 2% accuracy. However, he has no interpretation for this constant. The way he introduces this constant is in this famous paper here, delivered to the Physical Society. And the kind of key paragraph is, we consider the distribution of energy E over n resonators of frequency nu, and this is the most essential part of the whole calculation. E is to be composed of a very definite number of equal parts. We use the constant of nature 8. There H, there too, the constant H multiplied by the common frequency nu of the resonators gives us the energy element epsilon. Dividing the total energy E by epsilon, we get the number P of energy elements to be divided over n resonators. And then here's the one they don't quote. If the ratio of P is not an integer, we take for P an integer in the neighborhood. So this is obviously kind of a hedging on whether energy is really quantized, but he obviously did introduce discontinuity into physics and started this whole revolution in the direction of understanding quantization. Actually, Planck writes nothing more about black body radiation for the next 6 years. He doesn't accept quantization of energy until 1909, well after Einstein's seminal work. So Einstein is actually the famous quanta of light paper of March 1905, before special relativity. It's the only serious response to Planck that I'm aware of in the literature. And he says in the introduction that the observations of black body radiation, the photoelectric effect, et cetera, can be understood by the assumption that the energy of light is distributed discontinuously in space, consisting of a finite number of energy quanta, et cetera. Okay, but he starts the paper showing what Planck ignored. So he writes the Planck relation between the resonator energy U and the spectral density of black body radiation, same formula. He has R over N there, which is Planck's constant, K. So this is the equipartition theorem for the average energy of the resonator, and you get the Rayleigh-Jeans law, what we now call the Rayleigh-Jeans law, even though it was written down first by Einstein. And, he then notices the obvious fact that if you integrate over all the frequencies, this is infinity and there's something very wrong here. And he says, Thus, a definite distribution of energy between ether and matter is impossible. So what he then does next is he doesn't actually accept Planck's law as established. He uses the Wien limit, which is actually the quantum limit, and makes entropic arguments for particulate quanta that I won't go into. And then he presents experimental evidence for his conjecture through several things, but particularly the photoelectric effect. The photoelectric effect, he derives a simple conservation of energy equation that says that the stopping voltage for the photocurrent should be a linear function of the frequency nu with this weird combination of constants, which is h. He knows about h, but he doesn't use h. Okay. And this indicates that you can measure directly in the photoelectric experiment h and this prediction of the quanta theory. This is not an easy experiment. It took Millikan 11 years to get there, but here's his nice linear data on the stopping voltage versus frequency. And I love it. They put the little, like handwritten estimate of the slope in the figure. We don't do that anymore. And it's very close to Planck's constant if you recognize that number. Most of you probably know that Einstein won the Nobel Prize in 1921 for services to theoretical physics, unspecified, and for the law of the photoelectric effect. However, this was not an acceptance of quanta of light. They were not accepted till 1925. This was essentially a political story that, you can read about. Anyway, another thing that's not often mentioned as important to quantum mechanics, but I believe it is that in 1905, in his other famous paper on special relativity, he said that there was no need to have an ether for light to propagate in. And then later in 1907, he elaborates and he says, electromagnetic forces appear here, not here in his theory, not as states of some substance, but rather as independently existing things that are similar to ponderable matter and share with it the feature of inertia. So it's really thinking of them as particles, independent particles. Now, all previous waves had been thought of as a disturbance in a substrate, like this wave on a string. And the problem is that it's brilliant to imagine that there could be a wave without a mechanical substrate, but you immediately introduce the problem of non-locality. Because if I have a disturbance which is extended, it can go through both slits at once. But if I have something that has a particulate character, then that you get all the problems you've all probably heard about and studied and thought about and so on. Okay, so the next thing that Einstein does is that, and you see it's very soon afterwards, he accepts that Planck's law is correct, and he writes a paper on the specific heat of solids. And in the introduction, he says in this very Einsteinian way, for although one has thought before that the motion of molecules obeys the same laws as that hold for our motion of bodies and our world of sense perception, we must now assume that they can only assume fewer states and have only the energy h nu, 0 h nu, 0 h nu, 2 h nu, etc. So this is a clear statement that you won't find anywhere else of quantization of energy in molecular motion. He's taking the bull by the horns and saying, this follows. This has to be true now. And then he writes down this simple model, the Einstein model for the specific heat, and takes its derivative, treating them as independent oscillators, and gets the specific heat, which has the property that at high temperatures it agrees with the Dulong-Petit law that follows from the equipartition theorem, but at low temperature it goes away and goes to zero in contradiction to classical mechanics. And he fits it, actually, to this data here for diamond. And this catches the attention of Walter Nernst. Walter Nernst was an incredibly influential German physical chemist. There are many fun stories that I don't have to tell you about, don't have time to tell you about. But he decides that Einstein is Boltzmann redivivus, which means reborn. And he visits him and then starts to talk about him. Says Einstein's quantum hypothesis is probably the strangest thing ever thought up. If correct, it opens entirely new roads for molecular theory. And of course, Nernst was Planck's colleague, but he calls it Einstein's hypothesis. So if you're in that kind of competition, that's an interesting thing. The next thing that Einstein does is also very important, and that's he finally gives his first lecture to a group of physicists ever in Salzburg in 1909, and there he presents the result of a quantum fluctuation analysis. He looks at the quantum fluctuations to the momentum fluctuations of a mirror pendulum in equilibrium with black body radiation, and he derives this formula. Delta squared is the variance in the momentum of the mirror, and there's a term here which is clearly a particulate term. It's the momentum of one photon times the density of photons. The other one isn't as clear, but there's no explicit H in it, and it turns out to be the classical term. And this is analogous to a familiar thing in quantum optics, where the variance of the number density goes like the number density plus the number density squared. Okay. So this is an exact result in quantum statistical mechanics. If the black body law is true, which it is in quantum mechanics, then this is also true from fluctuation formulas in statistical mechanics. So he derived an exact, with no Schrödinger equation, nothing, he gets this exact result. And the fact he does, of course, interpret each term as one being a particulate and the other being a wave-based term, and he says, therefore, in my opinion, in the next stage of the development of theoretical physics, there'll be a fusion of the wave and particle theories of light. This is not accepted well at the time, I can tell you. He then spends 2 years trying to describe light quanta by modifying Maxwell's equation and fails, and then he turns his attention to general relativity, just as the Solvay conference is called. There's funny stories about that I have to skip, but you can ask me about them. Anyway, so he's going away, but Lorentz and Planck and Nernst have all accepted finally there has to be quantization of energy, and there needs to be a fundamental change, maybe in mechanics, maybe in electromagnetics, maybe in both. Okay. Now, at the same time, in same year, 1911, there was the famous scattering off metal foil experiment overseen by Rutherford with Geiger and Marston, where they discovered this remarkable high-angle scattering, which then said that the atom must be the seat of an intense electric field to produce such a large deflection in a single encounter, meaning there's a nucleus to the atom. So we have the solar system model of the atom, and this gives a clear classical picture that you could now try to quantize. Whereas before that, there were many weird models of how the charge was distributed in the atom. But there was no treatment of the electrons by Rutherford in this work, but that then became the work of his young collaborator, Niels Bohr, who learned about Solvay and, of course, knew about the solar system model early and adopts it to try to quantize the atom. He notes the probability that if electrons are going in orbits around a solar system nucleus, that they should be radiating because they're accelerating, and this leads to an instability, should lead to an instability classically. And so he says it seems necessary to introduce into classical electrodynamics Planck's constant, the quantum of action. So you need a quantization rule for this system. People knew that, but they didn't know which way to go. One of the puzzles is that the energy for an oscillator is some integer times h nu, and nu, the frequency of an oscillator, is independent of energy. The orbital frequency depends on the energy as this power. And you can go ahead and put this into E equals nh nu, and you don't get the right answer. But if you put it into nh nu over 2, you do get the right answer. And so you get that the energy levels go as 1 over n squared, and you put in all the constants you know, and it turns out to be consistent with the Rydberg constant to reasonable accuracy. So the factor of a half is an inspired guess, okay? And he doesn't analyze why this is stable to radiation. It's stability by fiat. The frequency of the emitted light is, as you would expect from Einstein's approach, the difference in the energies divided by h. Similar then to the oscillator, but many different frequencies will be emitted because of the spectrum of hydrogen is not uniform. And he predicts the various spectroscopic series, the Balmer and Paschen series that were known, the Lyman series that wasn't known, and the spectrum of singly ionized helium, etc. I won't go into the details. Einstein much later said how impressed he was about this. I'm going to comment to that in a moment. He said this is the highest form of musicality in the realm of thought. But what Bohr didn't say, sometimes misrepresented, is that the energy that goes out as equal to h nu is not a light quantum. It's not a photon. Bohr was always a passionate adherent of continuous electromagnetic fields. He even made a kind of joke at Einstein's expense, and I have to tell you later, about this, and he never accepted that until 1925. So he didn't say that there were photons, and he didn't describe the physics of the quantum jumps. In fact, he seemed to insist that they were instantaneous and sort of not describable. He does come back to the fact that the frequency of the light emitted by the electron doesn't seem to be related to the orbital frequency of the electron. And as we know, we didn't have this problem with the quantized oscillator. When charged particles oscillate, they emit light of the frequency of their mechanical oscillation, which seemed not to be the case for Bohr's atom. And this was really surprising, and Einstein's reaction when he heard about it was, well, then the frequency of the light does not depend at all on the frequency of the electron? This is an enormous achievement. The theory of Bohr must then be right. But if you read a little more about it, I think he found it very strange and really bothered him. And the reason was, how can we have a physics where charges accelerate and they don't radiate? I mean, this is like something that would have to create, a gravitational field in general relativity and so on. So it's a fundamental problem that troubles the field for the next decade. Pretty soon, the Bohr quantization rule, which is ad hoc, is replaced by Sommerfeld's quantization of phase space action PdQ, which is the angular momentum, which is often how we teach this now when we teach the simplest version of the Bohr atom. And this is sort of a general rule, and Einstein picks it up in 1917 and provides a topological version of this rule. But at the end of this paper, which I've studied carefully, he says, most systems aren't like this. They don't have enough constants of motion to apply this to. They're not integrable. And you can look up this article in Physics Today from 20 years ago where I talk about this. So that's the state of the field when Einstein really gets done with general relativity and gets back into it. And he just says, let's look at emission and absorption of light between two energy levels in an atom. So one process is going to be the absorption process, where the electron's excited, and there'll be a de-excitation process, which is stimulated emission, which is also classical, and those occur at the same rate. But he also posits that there'll be another process, which is a spontaneous emission. Now, here he's introducing a random acausal event into quantum theory for the first time. Why is he doing that? Because he has worked it through and he realizes that when you balance emission and absorption so you remain in equilibrium, you get the Planck radiation law. And so he's very excited by this. He says the light quanta are as good as established, but then he kind of thinks about it all, and at the same end of the same paper, he says the weakness of the theory lies that on the one hand, it's not bringing us closer to the union with the wave theory. On the other hand, it leaves the time and direction of the elementary processes to chance, but I still have full confidence in this approach. Later, he comments, I'm really not happy giving up full causality. So this is the point where the two paths towards quantum mechanics diverge. Bohr and Sommerfeld spawned the matrix mechanics school with these famous names associated with it. And they work on elaborations of Bohr orbits to try to understand somehow the frequencies, dispersion theory, and the Bohr-Kramer-Slater theory, which I don't have to go into. And then finally, the Heisenberg-Born-Jordan operator equations of motion successfully. I hope there'll be more on this elsewhere. In the wave mechanics branch, we have de Broglie, Bose, and then Schrödinger. And I'd like to talk about that in my last 5-6 minutes. So de Broglie comes to this wave understanding of quantization. Matter waves have a frequency that we all know now is lambda equals h over p. He justifies this by a very bizarre argument that I will not try to encapsulate. I mean, it's like there's a phase velocity, and there's a group velocity, and then they work okay in Bohr orbits, but what these are, he doesn't really make clear. But anyway, Einstein sees this, suddenly a light bulb goes off. He thinks this is probably the right direction. And at the same time, he gets involved with Bose, I'm going to tell you that in a second, with quantum statistics and mixing in de Broglie's ideas to get to indistinguishability. And then finally, Schrödinger, the wave equation for electrons, etc., Born interpretation of psi being the last piece. So a few more details about that right-hand branch. So in June of 24 rather, Einstein, who's now the most famous person in the world, or definitely the most famous scientist, gets a letter with an article by an unknown Indian physicist who says, look, I've sent you this article. I want your opinion. He also wants him to translate it and publish it. And though a complete stranger to you, I do not feel any hesitation in making such a request because we're all your pupils, etc. And of course, I mean, you would think this is like a 1 in 1,000 or that million shot that this gets noticed. But it gets noticed, and Einstein somehow thinks this is the right thing. So the problem that Bose was going back to was deriving the Planck distribution just looking at a photon gas, not looking at resonators and that whole other route. And it was known from Ehrenfest and de Broglie that this doesn't work when you use classical statistics. In this work, which this is not, well, this is some recent translation, etc., what he's doing is he's counting the phase space cells in which you can put quanta of light, and then he's counting how many of them are, and he's going to get, again, an entropy and figure out the distribution from that. And here's the formula that he used, and this looks very similar to the occupation number representation that we now know in many bodies, with all these factorials in the denominator. It's not exactly the same, but it has the same property. It neglects interchanges of identical particles between cells. There's no comment of any kind as to the meaning of this formula. He just says, this is it, and goes ahead and gets the Planck formula. And then many years later, he said, I had no idea that what I had done was really novel, that it was different from what Boltzmann would have done. But Einstein immediately says, in my opinion, Bose's derivation signifies an important advance, and he then submits a paper within 10 days using Bose statistics to analyze the classical ideal gas. And he gets the right equations, but he only partially solves them. And it does demonstrate deviations from the ideal gas law, loss of entropy, etc. But it seems he doesn't actually realize the radical nature of the statistics. I think he just used it because he writes to Ehrenfest, the essence of this is still obscure to me. Okay, but 6 months later, after a few more letters, he says, the thing with the quantum gas turns out to be very interesting. Much of what is true and deep is lurking behind it. By January 25, he publishes the full theory of the Bose gas, including condensation of molecules into the quantum state numbered 1 without kinetic energy, etc. And he points out that the particles are not independent. He says, Bose's statistics expresses an implicit hypothesis about the mutual influence of molecules of a totally new and mysterious kind, which is the bunching that we know well. He still doesn't discuss the interchange of identical particles. He goes on instead to derive a fluctuation formula now for massive gas molecules, an exact formal analogy to his 1909. And now, of course, it's the wave part that's the new thing. Okay. And after presenting that, he states in this paper, the presence of interference fluctuations is more than just an analogy, since a material particle can be represented by a scalar wave field, as de Broglie states in his remarkable thesis. This oscillating field, whose physical nature is still obscure, must permit itself to be demonstrated by diffraction phenomena. And then he goes on to talk about looking for matter wave diffraction, but he also has calculated how incredibly small the wavelength will be, so he said it's going to be very hard to see. Okay. In 1925, Erwin Schrödinger, who's gotten to know Einstein, writes him a letter suggesting there's an error in this BEC paper. Here's Einstein's reply. Your reproach is not unjustified, although I've not made a mistake in my paper. In the Bose statistics which I use, the quantum molecules are not mutually independent objects. And then he writes, I love this, he writes this little diagram. Can you figure out what that is? That's two particles in two levels. Einstein and Schrödinger sharing two particles in two levels. And he points out that on the Bose statistica on the left, the two interchanges are treated as one. So he clearly understood this. I don't know why he didn't say it in the paper he wrote. So this loss of identity of identical particles pushes towards non-locality in quantum mechanics and lack of identity. I'm really close to ending now. So Schrödinger says, I had not grasped it before at all, despite the fact that Bose's paper had already come out. That work didn't seem particularly interesting to me. Only your theory of gas degeneracy is really something fundamentally new. So he reads de Broglie's thesis in November, writes a second paper on Bose-Einstein statistics himself, where he says the particles are the foam on the wave radiation that forms the world. He's already working on finding wave equations. Later, he states wave mechanics was born in statistics. So this is the famous first of the 6 papers from January 1926. Of course, getting rid of Bohr orbits and having stationary states, eigenstates of the hydrogen atom. Introduces the time-independent Schrödinger equation, calculates the hydrogen spectrum. Pauli had only just done that within 2 weeks of him using matrix mechanics. And in March 1926, he proves that waves mechanics is equivalent to matrix mechanics, which is also done by Pauli independently, and gives de Broglie and Einstein credit for stimulating his theory. In June 26, he then introduced the time-dependent Schrödinger equation with the mysterious I in the right-hand side and calculates the dipole moment oscillations of the atom to justify the Einstein rule. And he describes psi squared as a weight function, but he doesn't accept that the Born description as a probability density. He still hopes that these waves are real, the real thing. Okay, so in summary, the key step in both the matrix mechanics and wave mechanics is giving up on the classical trajectories in the atom to describe particles by functions. It was harder for Heisenberg because he didn't know he was looking for a function. He was just sort of free associating, as far as I can tell, with some hints from Born and so on. Schrödinger knew he was looking for a wave function, but he didn't know how he was going to interpret at the end. Quantum mechanics is often criticized for destroying intuition, but here I want to emphasize quantum mechanics restores our intuition about radiation-matter interactions. In a stationary state, the charge density rho, E side squared, is not accelerating. It's time-independent. Only when you're transitioning between states and you have a superposition do you have an oscillating charge density in quantum mechanics, and it oscillates at the energy difference. So Einstein was right. That had to be there somewhere. Okay, so next 100 years, I'm not going to go into it, but I'll just say that I'm so impressed with the new understanding of quantum mechanics, entanglement, essential non-locality, violation of Bell, decoherence is a loss of information, entanglement is a resource, quantum computation, robust theory of measurement. I would say no quantum classical boundary. I would say no collapse of the wave function, and we maybe argue that part out. So, we're going to, that's what we're going to do in the rest of this. So I do want to give Rob credit for this statement that it's not the collapse of the wave function, it's the collapse of the physicists. But anyway, so in conclusion, just a moment of reflection of this spectacular set of achievements, a quote from Max Planck: "If any thought strengthens and elevates us during the patient and often modest work that demands our mind and bodies, it is that in physics we labor not for the day, not for momentary success, but as it were for eternity."
Thank you very much, Dr. Chan. We have time for maybe one very brief question. If somebody wants to ask a question. Yes, one. Okay, quick.
So you,
It's on.
so you mentioned Heisenberg's ideas in June 25, and then the solution of the hydrogen atom in that sense only in January 26.
That is correct.
Right. So I sort of knew that was correct, but then people asked me in coming to this conference, what did Heisenberg actually find that it was clear that he was onto something back in...
Well, he quantized the harmonic oscillator and the anharmonic oscillator and used perturbation theory to see that he got sort of known results for that. I don't know what he was comparing to. And he showed that his operator equation of motion conserved energy, again, to some order, et cetera. So he wrote these matrices, and it was essentially equivalent to commutator of H with the operator X is equal to
So basically the harmonic...
dxdt. Yep.
Basically the harmonic oscillator.
Well, and some of the properties of the time evolution. But look, this is the part I don't know, and I think there are people here who know it much better than me. I've read this nice thing that I recommended.
Sorry that I have to be the quantum mechanic to cut the discussion off. Sorry. Otherwise, we'll be kicked out of the hall. So let's thank Doug one more time.